My dear students, I am Sunira from Department of Physics, Government College, Madapalli. This is lecture 2 of particle physics. This is part of MSc Physics syllabus of University of Calicut. In this lecture, we will learn about electromagnetic weak and strong forces. So, we already learned in our degree classes all about electromagnetic forces. In this lecture, we just recall all these things we learned in our previous years. So, the electrostatic force was formulated by Charles A. Coulomb. This happens nearly a century after the formulation of gravitational theory by Newton. So, Coulomb formulated the electrostatic force just like gravitational force. In this case, Coulomb proposed that the Coulomb force is proportional to the product of product of the two charges and inversely proportional to the square of the distance between them. And he gave the formula such that this force F is equal to K Q1 Q2 by R square. This is the magnitude of the force. Here K is a constant which is given by 8.987 into 10 raised to 9 Newton meter square per Coulomb square. Then electrostatic force can be attractive or repulsive. In our previous lecture, we learned that gravitational force is always attractive. In this case, electrostatic force can be attractive or repulsive. If the two charges are same polarity, if both are positive or both are negative, then there is repulsive force, otherwise there is attractive force. Similarly, if the charges move, there appears magnetic force. So, James Clerk Maxwell unified these two forces and called it as electromagnetic force. Those equations are known as Maxwell's equations. You learned well all these in your electrodynamics class. Now, the magnetic force between moving charges can be manifested as direct consequence of electrostatic force using the special theory of relativity. So, these two forces unified into the electromagnetic force. The impact of these forces are the atoms and molecules are held together due to this electromagnetic force. Similarly, all forces within the living organism mainly emanate from this electromagnetic force. The different types of electromagnetic radiations arise due to this electromagnetic force. Similarly, any change in the velocity of a charged particle causes emission of radiation or emission of photon. Photons are the carriers of electromagnetic force. But neutrinos and gravitons cannot be affected by these electromagnetic interactions. Electromagnetic interactions can affect particles even if they have no charge. But neutrinos and gravitons are exceptional cases. In chargeless particles. For example, neutrons. Neutrons are neutrally charged particles, but they are influenced by magnetic fields because they are magnetic moment. Okay. Similarly, in the case of photon and neutral pion, as all of us know that photons and neutral pions are they have no charge and they have no magnetic moment. But photons are created by electromagnetic interaction. Similarly, pair production. Pair production is mediated by electromagnetic interaction. Similarly, decay of neutral pion into two photons are also driven by this electromagnetic interaction. Okay, so in this few slides, we reviewed all the things about electromagnetic force. Here, electrostatic first, the theory was developed by Coulomb, electrostatic force. Then Maxwell merged electrostatic force with magnetic force. Then comes electromagnetic force. Then we check its relevance and conclude that even if the particle has no charge, they can be influenced by electromagnetic interaction, except neutrinos and gravitons. Okay, so we can move on to next interaction. The second interaction is called weak interaction. Okay, so in this case, the radioactivity. In the case of radioactivity, the beta decay happens. This beta decay is explained based on this weak interaction. In the case of beta decay, there is a conversion of neutron into a proton or vice versa. Okay, so decay of pion into muon or and muon into an electron. All these processes are mediated by weak interaction. Neutrinos are only affected by weak interaction. Neutrinos are only affected by weak interaction. But still, the probability of occurrence of weak interaction is very low because weak interaction is very weak force. The range of this weak interaction is very low. It is nearly 10 raised to minus 17 meters. 10 raised to minus 15 meter is called Fermi. Here its range is less than 1 Fermi, less than the size of a nucleus. 10 raised to minus 17 meters. Now, earlier scientists thought that the emission of neutrino was characteristics of the weak interaction. When weak interaction happened, there happens the emission of neutrino. But later they found that in the case of many decays of strange particles, there is no emission of neutrino. So, but still, this decay of strange particles are weak interactions. So, the neutrinos are only affected by weak interactions, but it doesn't mean that all weak interactions emit neutrino. The decay of strange particles, in the case of decay of strange particles, there is no emission of neutrino. Okay. So, the theory of the weak force has undergone many developments later. Now we can move on to the different stages of developments of the theory of weak force. In 1934, Enrico Fermi formulated the theory of the weak interaction. And in 1958, R.A. Marshak and E.C.G. Sudarshan. E.C.G. Sudarshan is an Indian scientist. They pointed out that these interactions involve an action between two currents. This is just like attraction or repulsion between two current carrying wires. In analogy with these electric charges, scientists proposed that there is weak charge. In the case of electromagnetic force, there is electric charge. Similarly, in the case of weak forces, there is weak charge. Later, R. Feynman and M. Gilman further found that these weak currents are partially conserved. Later in 1957, Julian Schwinger qualitatively pointed out a possible way to unify the weak and electromagnetic interactions. His research student Sheldon Glashow pursued this idea further and went on evolving the theory for years. The similarities between the weak and the electromagnetic currents leads to the unification of these theories in 1960s and 1970s. Another research student, Gerard Thorft, later managed to solve the mathematical difficulties which blocked the theory for its final acceptance. Finally, the theory is unified, which is called as Electroweak theory. The unified theory of electromagnetic interaction and the weak interaction together called the Electroweak theory. This theory is known as Weinberg-Salam theory. Steven Weinberg and Abdus Salam independently published the principles of this theory in 1967 and 1968. Now, what is this Weinberg-Salam theory? The electroweak interactions are carried by four bosons, one positive, one negative, and two neutral. So, Weinberg and Salam proposed that these electroweak interactions are mediated by four bosons. Two of them are charged, positive and negative, and the other two are neutral particles. These bosons are similar in very high energies, such as greater than 10 raised to 11 10 raised to 11 electron volt. 10 raised to 11 electron volt. So, the symmetry between these bosons are broken in moderate energies. The very high energies, there is a symmetry, and due to this symmetry, we can't distinguish between these four types of bosons. But when the energy is reduced, it comes to moderate energies, this symmetry broken, and we can distinguish these particles. Three of the particles are massive and they are W plus, W minus and Z0, neutral Z particle. And the fourth particle is known as the photon, which is the massless carrier of electromagnetic interaction. Okay, so in the Weinberg-Salam theory, in the electroweak theory, the theory itself brings the carriers of electromagnetic interaction. The unification of these two theories happens only on very high energies, which is greater than 10 raised to 11 electron volt. The carriers of electroweak interactions are four, three of the massive and one massless. So the photon, the massless particle is the photon, which is the carrier of electromagnetic interaction. The massive bosons, that means the W plus, W minus and Z0 have their masses between 80 to 100 GeV, giga electron volt. So the weak interaction is mediated by these bosons. The range of the interaction is very short because their carriers have very high mass. So, the electromagnetic interaction is mediated by photons. They have no mass, so the interaction has infinite range. Then the weak and electromagnetic interactions have common source, but they differ in their proper practical cases. So we can treat them as different interactions, electromagnetic interaction and weak interaction. For our purposes, always energy is more in moderate range, not in the range of 10 raised to 11 giga electron volt. So in this context, the electromagnetic interaction and the weak interaction are two different phenomena. So we can treat them as different interactions. Now, what are the experimental evidences for this weak theory? The best experimental evidence would be the detection of these massive bosons, which are predicted by the theory. These massive bosons are called, these carriers are called intermediate vector bosons or weakons. In 1973, the neutral weak currents were discovered at CERN and Fermi Lab. CERN as the accelerator constructed by this European Union, and this CERN, the neutral weak currents are first detected. Neutral weak currents were first detected at CERN and Fermi Lab. Okay, now in 1979, Salam, Weinberg and Glashow shared the Nobel Prize for the electroweak theory. But still, the carriers vector bosons were not detected. In 1982, the first signs of the intermediate vector bosons were seen at CERN, with right mass and other properties predicted by the electroweak theory. So these are the important things in connection with the electroweak theory. Now we can move on to the strong force. In this case, the strong force is also a short range attractive force. This happens between the nucleons. And all of you know the nuclear force does not depend on electric charge. And the force is the force responsible for the stability of the nucleus, the nuclear fusion, and the creation of particles in collision between two nucleons and between a nucleon and a meson. All these happens due to the strong force. Okay, we already discussed that in the case of atoms and molecules, their stability depends on the electromagnetic interaction. But when come to the nucleus, the case of nucleus, the nuclear force decides the stability of nucleus. Okay, so for the stability of nucleus, there should be nuclear force. The strong force does not influence the electron, muon, and the neutrinos. Similarly, the carriers of electroweak and gravitational interaction. The theory for the strong force was put forward by H. Yukawa. In 1935, H. Yukawa published his theory of nuclear force or strong force. It is a short-range force of the order of Fermi or 10 raised to minus 15 meter. Okay, the case of weak force, it is of the order of 10 raised to minus 17 Fermi. But here the strong force is the order of 10 raised to minus 15 Fermi. So Yukawa's theory is identical to the electric force, but multiplied by an additional factor. This becomes very small when the distance between the centers of the nucleons exceeds a certain limit. He proposed that the field of the strong force produce some kind of particles. Later, These particles are known as pi mesons or pions with mass 100 MeV. So, the carriers of strong force are called pions or pi mesons with mass 100 MeV. Now, what are the limitations of this theory? In this case, in the case of Yukawa's theory, it is not clear that the force between the two nucleons is along the shortest line between them. That is the first drawback. The second one is the strong force between nucleus is influenced by the presence of other nucleons in its vicinity. But the theory does not discuss this case. Then comes the next property of the strong force. The strong force depends on the direction of the spin, but Yukawa's theory uh, cannot account this spin of the particles. The theory does not reflect the fact that the force is attractive only for distances greater than 1.2 Fermi. If the distance gets reduced, there is a strong repulsive force which is known as hardcore repulsion. This hardcore repulsion you learned in your quantum mechanics class, hardcore repulsion. So here that is what happened. In the case of the nuclear force, when this distance is greater than 1.2 Fermi, the force is attractive force. But when it less than this 1.2 Fermi, the force becomes repulsive such that hardcore repulsive force. And finally, unification of all these interactions are proposed. This theory is called Grand Unified Theory. In this model, the electromagnetic, weak and strong interactions are unified. This would happen only at very high energies of the order of 10 raised to 16 giga electron volt. According to this model, proton should decay, but this is not observed yet. Similarly, gravity cannot merge with the other forces. If it happens, the theory is called theory of everything. Similarly, the scientists believed that at the time of Big Bang, in the beginning of the universe, all of these interactions are unified into a single one, and as the universe cools, all the interactions separated. And then comes the four fundamental interactions: gravitational, electromagnetic, weak, and strong interactions. And finally we can conclude our lecture here. In this lecture we learned about electromagnetic interaction, its developments and the properties of the interaction, its importance in this universe. Then we move on to weak theory, its developments, the properties, its relevance and its limitations. And then the unification of electromagnetic theory with weak theory, which is known as electroweak theory. And then last one is grand unified theory and theory of everything. So in this lecture we learned about the three fundamental interactions. One of the interaction, gravitational interaction, was the in the case the gravitational interaction. In the previous lecture, in our first lecture, we learned about gravitational interaction. But in this lecture, we learned all other three interactions: electromagnetic, weak, and strong interactions. Okay, so you have to learn well and review all your previous knowledge about all these forces very well. And if you understand all these things very well, you can find out, you can write short note about all the things we have mentioned in this slide conclusion. Okay, so learn well. So if you need further information about these things, please read these articles. The first one, the particle hunter by Niemann Weikirch, is your prescribed text in your syllabus. The second one, Fermi and the Theory of Weak Interactions, the general article published in Resonance in January 2014. And the last one is an article which can be seen in the worldscientific.com. In this one, you can understand the difficulties and the experimental setup, how the scientists discovered the W and Z bosons in at CERN lab. Okay, hope that you can understand the fundamental forces, the four fundamental forces in nature, and all the things you know previous will recall here. Okay, so happy learning. Thank you.